If you start counting 1, 2, 3, 4, and so on forever, you would count an infinite number of numbers. This is called countable infinity. But there's also an infinite number of numbers between 0 and 1. More, in fact. As Cantor proved in his famous diagonal proof, the infinity of numbers between 0 and 1 is actually bigger than the infinity of counting. It's called uncountable infinity. These numbers, unlike ordinary counting numbers, go on forever. There is no final digit to pi or to the square root of 2 or to 0.12121212 and so on and so forth. But this argument also holds true if you switch the numbers around and put the decimal point at the end of the number. These new numbers, with the infinite digits going off to the left, are bigger than countable infinity. After all, each one can be paired up directly with an irrational number. This means that if you started counting, you would never reach one of these numbers, even if you counted forever. But what are these numbers like? First of all, it's impossible to compare their sizes. How do you know if this number is bigger or that one? There's no first digit to use to compare them. However, addition and subtraction both work. You just use the standard algorithms. Multiplication works too, it just takes longer, which is actually the same amount of time due to the nature of infinity. Division is difficult, if not impossible, because division is about comparing the sizes of numbers, and these numbers have no size. There's no first digit, and nowhere to start doing any sort of division algorithm. One of these numbers that I find particularly interesting is 99999 repeating. The corresponding irrational number, 0.99999 repeating, just equals 1, as you can see in this proof. But this number clearly does not. If you add 1 to it, however, you get this, an infinite string of zeros with no first digit. I'll call that number theta, because it kind of looks like a 0, but not quite. Theta is clearly infinite. If all of these numbers are the same size, how could it equal 0? That would be less than all of the other numbers. If you subtract 3 from theta, you get this, which is clearly not negative 3. However, if you add 3 to theta, then you get an infinite string of zeros before a 3, which is technically just another way to write 3. In other ways, theta behaves just like 0. If you multiply theta by anything, you just get theta. Remember how earlier I said that 99999 repeating doesn't equal 1? I'm no longer so sure. First of all, 99999 plus itself equals 99998, and if you add 1 to 99998, you end up back at 99999. There's only one number that makes this equation, x plus 1 equals x, true. That number is negative 1. Since theta equals 99999 plus 1, theta would indeed equal 0. Maybe this is why ancient cultures weren't sure what to do with 0. It's far stranger than any other number, be it whole, infinite, or irrational. Theta turns the number line into a circle where infinities continue out forever and leave you right back where you began. But if theta equals 0 and 99999 equals negative 1, we know that 99998 would equal negative 2. In fact, we could continue this process and assign infinitely long numbers to every whole number on the number line. But there are only countably infinite whole numbers and uncountably infinite infinitely long numbers. So after assigning 1 to each tick on the number line, you'd still have infinitely many left over.